Hello, hello, hello. As always, the way I start. Does it work? Does it work? Hello, hello, hello. Ah, it does, but I'm on the wrong thingies. Let's just try this again. Is it that one? It does, but I'm on the wrong thingy. And finally, I probably need to make it a little bit louder, maybe? Maybe not. Maybe I just need to turn my volume up. Yes. That'll be it. Okay, cool. It's been a while. I went on holiday for like a whole month. And whilst I was on that holiday, or actually even before that, I was doing game development. Totally lost motivation because I got stuck on something. So on the side of that, I've always been like trying to get better at maths. I'm not sure how that's going, but we shall see. I feel more confident. That doesn't mean I'm right. So just to remind everyone, I know nothing, so this is me just learning. Um, and the goal is already explained a million times. If someone actually asks me, I'll explain. I usually start off with a Greek lesson. Um, yeah, we can do that. Why not? Hey, why not? Actually, you know what? No, let's do it. Let's not break the way things worked before. Ooh, new features, eh? Let's see. Duolingo Plus is now Super Duolingo. New look and name. Same fun features. Alright, cool. Alright, cool. That's great. Let's go to Greek. Yeah, I'll have to probably remind myself of how this all is. So let's just do that.
Ria.
Ria, this is an R, yes.
Ze.
Z.
Ze.
V.
Vi. Na.
Na. Z.
Ve.
No.
Ze.
Ooh, okay, so fair enough.
Ze. Ze.
Cool. Ria,
Ria.
that one again.
Na.
Na.
Na. Vi.
Is it ma or na? Can't remember now.
Vi.
V. V. Guess it's
Vi.
that one.
Vi.
V.
Vi. Το mini market.
The mini market. It's good that it
Ria.
sounds like English, isn't it?
Ria.
Na.
Να. Ναι, το mini market.
Ne. Yes. The mini market. Oh, that's right. Oh yeah, cool.
Μα.
Ma.
Μα. Mark το mini market.
Mark the mini market. Ma.
Να.
Oh. Whoops. Haha. Nay.
Ναι.
Nay. Na.
Να.
Na, ma,
Μα.
ma, an,
Παν.
ria,
Ρία.
ria. Select the correct characters for an, that
Παν.
one. Select the matching pairs. Ro,
Προ.
an,
Παν. Να.
Select for ma, that one.
Μα.
Alright, cool. Greek's done. Skip. Cool. Start your progress. Enjoy, no. Oh, I don't care. Just let me out now. Continue. Cool. Right, closing that. Yeah, so when I was on holiday, I was doing my first machine learning model. It was only a perceptron, but it was fun nonetheless because now I realise the perceptron is that little sigmoid part, or I think it's the L in this kind of book that I'm reading, and I realise that now they're going into this Adeline equation, which is like backpropagation version, and it just replaces that loss function, I think. But there's something about partial derivative, and I have been trying to understand all the maths going through this. Let's not talk about how long it took me to understand the perceptron maths. So I thought I'd like to know where how these equations were manipulated. I have been learning just simple differentiation and partial differentiation using the product rules and all that stuff, quotient rules. But actually, I couldn't get this one to work, and I did find another thing called chain rule, which might be applicable here. So there's a couple of mathematical things I'd like to get used to. So I guess I do have to explain why, even to myself, because machine learning will allow me to make predictions rather than process all physical properties of electrons and their forces that are applying to each other. I need to know that because proteins are made of elements, and elements are made of electrons and protons and neutrons. Um, the way the proteins fold denote functions, and that's why I need to know how they are going to unfold. I know AlphaFold, which is DeepMind's bad boy, uh, has been created and is very effective. I suppose I don't want to use it if I don't know how it works. So that's that. And then when I know uh, which way a protein is going to fold, um, I can start to put real proteins into my machine learning and then kind of new newly programmed proteins into my machine learning model and see how they'll fold. And then I wanted to link that up with DNA sequences. So what does a DNA sequence how does a DNA sequence work? We did some of this like at the beginning of last year or whatever, and that's important because then I can know which proteins are going to be made, uh, and then we can start to engineer some biology. That's the whole thing, the whole plan there. Uh, and then the actual goal is to be good with it. Right. Regardless, let's start where I have been. So just a little recap for myself, and I'll treat this as a myself video, so I don't think anyone's really watching. Um, we did, or I did a perceptron um, model, and that perceptron model actually, I think it's explained here somewhere. God, where is it? Here we go. Yes. Yeah, okay, yeah. So let's load up whiteboard. If I can actually click the button right. Yeah, let's go here. I'm just going to go to dark mode because that is killing my eyes. Awesome. So, where's my white? Is it that one only? Um, in this document here, which I'm gonna put side to side with my whiteboard, it talks about this decision function. So, first of all, this sig, gosh, this sigma is a function that takes in an input, and that input, if I remember correctly, is the dot product of all weights, and I think it's plus a bias, so whatever that means. Um, so you put that into this, and it just says, hey, what's the dot product? Is it let's see, how do they lay it out? Yeah, if it's if uh, if that dot product is greater than or equal to 0, then do 1, return 1, otherwise return 0, right? So that's that part. And then so this is just explaining the dot product. I mean, I don't know if you can see that. I don't know why it's so bad quality as well. See if I can. Oh, here we go. Cool. It is good quality. That's fine. So I don't know why it's. Yeah. So yeah, this is the dot product of weights. I think X is like a feature in a data set. So if you had, I think their example is flowers. If I had a flower 1 and a flower 2, these would be examples because they're the rows in this data table. But then you've got like the features. So this would be x1, x2, yeah, and then it would be, this one would be x1 of 2 because there's 2, but this actually would be 1 in this case, and this one would be 2, right? This one obviously corresponds to this. So this might be like I think it's like petal width of a flower and uh, petal length, petal width, whatever. And then you have this class classifier. So this y value here, which is actually like if I am to have these two features, what should the y value be? Well, that was confusing when I was looking at this first of all, because it's not totally clear until you look at the code, and then you kind of look back over the math and you're like, okay, that makes a bit of sense now. But anyway, that's that. So just gonna go back a bit more. Yeah, it's just describing these weights are like arrays of um of things, and actually it's an interesting property here because this guy who's written this guy in the um, non-gender sense is saying that if you were to draw a normal distribution like this, like a Bell's curve kind of thing, they're just taking random numbers, on this Bell's curve, and I think the distribution is between like 0.001 and something. I think it might even say what it is. Anyway, they're just getting random numbers. So that because if you had this W, this weight as 0, then it would just all of the multiplications of the dot product would become 0 plus bias, so it would the maths wouldn't work. Yeah, okay. Yeah, so this is the sum of sum of all the dot products. Uh, no, sorry, the dot product. And then let's see. Oh yeah, it's saying that the perceptron only works if your data is linearly distributed, or uh, what does it say? What's the word it says? But basically, the data must be separable by a line, linear boundary, decision boundary, I guess something like that. And so this class 1 is still talking about the label. So if this example has two features, and the example has two features, and those features are related to a specific flower. That specific flower is labeled, I don't know, rhododendron. Y is rhododendron. So this is what these classes are: rhododendron and daffodil or whatever. It's just saying as well. This graph is saying, well, yeah, this basically. So if it's over 0, then return 1. Otherwise, return 0. Then it's talking about the updates. Now this is interesting because this walrus operator, this little colon and equals, I think I only first came across it in Python, so it's kind of helpful that I learnt Python because I now understand it that wj is rewritten with the new value simply because of the walrus operator. So that's kind of cool to know. How do I move down with this thing? Oh yeah, that's right. Actually, let me just delete this nonsense now. I think I could do that, can't I? Yeah. And yeah, because this is kind of important as part of our decision-making stuff. So it says wj, this is the new calculation, is equal to, is going to be equal to, or set to, the existing wj plus the derivative of wj, or the change in j. Yes, okay. Well, the change in j, I don't know if that really means the derivative. Not really. So let's just write that down because I remember myself. It's good to write things down. It gets in my head then. There we go. Plus change of wj. And this b, you see, b doesn't have an index, and that's because b is all. Oh gosh, b is always the same actually. So well, the constant is the same. Um, it's just that you are increasing it every iteration. I think that's right. Must be right. And so the update values, deltas, are computed as follows. So it says this little eta, eta is this little n thing. Um, that is a constant. I think that value in their case was set to 0.01 or something. And it's like, I think it was like the scaling of I think it was the scaling of something. I can't quite remember. Let me just see. The learning rate typically is the true class label of the ith training example and the predicted class label. It's important to note that the bias are being updated. Yeah, I think in any case it does some scaling on the graph if you were to draw it. Because I think originally I thought the learning rate was going to be like how many iterations I'm going to do, but it's not. It's like very much part of the decision making. Like how many times do you have to run it before you start to hit these boundaries set by the dub the decision function, and that's the note like that. The speed of that is denoted by this learning rate, if I remember correctly. And if you set it too high, it just it doesn't get accurate enough because it's already kind of gone like I think you're equal to many things rather than if you put in a flower and I've got this petal width and petal length, then I could be equal to many things. So yeah, so that's I think that's what it does. And this y to the ith indices minus well yi indice minus yi indice. This is saying if I go back to the I think I deleted the table now, but if I go back to this table, this is I plus 1, I plus 2, right? So all this is saying is go and get the class that it thinks it is, and then minus it by the predicted class. So the predicted class is that function up here. So this is the prediction that it makes. You're passing in y here, and then you're getting out, or yi, and you're getting out the output, which they've denoted as this. I think that's right. This xj is multiplication of the feature. So this is good for many features. Actually, it works across not just one feature, but as many as you want. Um, and this x is actually like a set rather than just a specific value because that specific value is like a row, and so there's lots of data in that row. Good. Um, it says which means that which means that we don't recompute the predicted label before the bias unit, and all of the weights are updated via their respective updated values. So it's saying that each weight is going to get updated. Um, that's it. That's what that says. So then it says, before we implement the perception rule, let's go through a simple thought experiment to illustrate how useful In the two scenarios of the perception, the bias unit and weights remain unchanged since the update values are 0. Yeah, okay, so that's just proving its case. Um, that's fine. Yeah, so linearly separable, that's the one. So it only well, it does work in other cases, but it does this funny, like I had this graph drawn and everything, but actually I don't think I've updated my computer with it now. Let me just double check. Tools. Let me see what I have in here. I don't think I've got it. No, I don't. That's not it. This is well out of date. Um, that's fine though. Okay. Yeah, so essentially, like, there's basically this updating that occurs, and when it goes for each like iteration of this model, if you're drawing a graph of like errors, it's actually got this on the next page, I think actually, maybe not. If you're drawing a graph of errors, it's like, okay, I'm wrong, so then I get weighed down by the dot product of the weights and the biases and the feature. And so then it's like, okay, I'm a little bit more correct. I'm a little bit more correct. And I'm a little bit more correct. And then I'm like totally correct then. But in the case of non-linearly separable in the perceptron, what what seemed to happen is, like, because I didn't even realize this at the time, it just kind of bounces up and down a bit. But sometimes it does level out and it does make the correct predictions. But they're saying that you can't rely on this. So obviously it's just kind of step one in the algorithm learning phase. And this is a nice little diagram here of what it is. So you've got these features. X of m is like n. I don't know why they use m, because it's like number of features, right? And then w is these Bell distributed um, randomized values. B is this constant, and you basically find the dot product and you pass it through. Yeah, net input function is the dot product. So this is like the sum of all the products, and then you pass that into your threshold function, and that gives you this new or predicted output. And then you pass this back in and you say, well, was that wrong or right? Because we can compare it to the class label. Oh, it wasn't right. Go back round and try, put in all the new numbers, because these have all been updated with um, this iteration, and then and so on and so forth, right? Oh, it's really hot today. Okay, I've got like a cooler down there, thank goodness. Um, Implements perceptual learning. Yes, then it takes you through the code, which isn't too interesting, but it is first time around because I was really struggling to understand what the heck was going on. So initialization, it sets this eta to this arbitrary number, but it's for that scaling thing I talked about. How many times it's going to iterate before it decides it's accurate enough. Um, Random state. I can't remember what that does. Then it's got this fitting function, and that fitting function takes your features. So it says an array of you know um, A, B, C. That's that. So that's that X, and then you've got this Y, which is just a single. Well, it says it here, an example. So God, so we go Y equals that, and this is going to be the kind of actual values per thing. So let's say this was daffodil and this was uh, whatever, rhododendron. Then it's going to be 0, and then actually I think 0 works, 1 and then 2. So this will be daffodil, and this one will be, because you can't do mathematics with strings. You have to convert them into numbers. So you just give it like an ID. So daffodil is 1, radiolindrum is 2, and so on and so forth. Maybe it does start from 0, I can't remember. Yeah, and then so this is this weighting. It's just getting from a normal distribution a random number between 0 and uh, the distribution is 0.01. Um, B is set to actually 0 at the start, so B becomes 0, and then errors is an empty array. And then it does a for loop through these iterations. Um, this zip thing is like it's like joining them into a single array, but actually it becomes x basically goes here, and then y is the target, and it goes here. But you're able to iterate over both at the same time, so that's why that zips there, I think. And then this is the update, so this is me. If I go back over here, that's this bit here. So you can see, well, hope you can. So eta is this, this thing that I didn't actually write, but it's that. And then target. Oh, actually, no, I didn't write the function down here. Where is it? Oh, I didn't write the function, but it's basically going to be something like this. So it'll be um, y I minus that of um, of, uh, of the feature, basically the dot product. So this is going to be um, sum of the products of x and w, something like that. And then yeah, so then this prediction is this, and so that becomes y output I, and then um, and then it increases it doesn't increase, it reassigns the value of the weight and the bias. So the weight is going to be the update, so that's whatever the kind of prediction was, and then multiplied by the feature, essentially. Yeah, that's cool. And then of course it says if it was right or wrong. So because there's only two different things, they're linearly separable. That means that there's only two things to calculate between. Then it says if it wasn't 0, then that means it was wrong. That was an error. So then it appends that to the errors. This predict and this net input. Net input is just the dot product of the weight and the bias. Sorry, the feature, the weights, and then plus the bias at the end. And this prediction was this thing here. If it's greater than or equals 0, do 1, otherwise 0. Via the fit method, we initialize to initial value 0 and the weights in self to a vector r of m, where m stands for the number of dimensions. Yeah, whatever. So I guess real numbers because vector. I can't remember why it's a real number actually. Yeah, and it says technically we can initialize the weights to 0, but I was saying like it doesn't actually work out. In fact, this is done in the original perceptron. But however, if we did that, then the learning rate would have no effect on the decision boundary. So if all the weights, the learning rate parameter eta affects only the scale of the weight vector, not the direction. If you're familiar with, yeah, I didn't quite understand this part actually, but it's saying that if you had an array of, let's see, so we've got V1, and that's going to be an array of 1, 2, and 3. Then the vector 2 is going to be 0.5, 1, and 1.5. And then if you find the arc cosine, so that's the cosine -1 of the dot products between V1 and V2 divided by Oh, I'm not sure what like linear algorithm normal of v1. The normal of v1. Oh, actually, I'm not sure what that does. Line or g norm. Line or g dot norm. And I need to get off this as well. Let's go back over here. Let's put that there. Except all. This function is able to return one of 8 different matrix norms or one of an infinite number of vector norms, depending on the value of the odd parameter. This function is matrix or vector norm. Normal. What's the normal of a vector? Yeah, okay. I guess it really does mean the normal then. See if there's any graphs. No. Um, there's loads of examples here. Is library functions used to calculate one of the 8 different matrix norms or vector norms? What are matrix norms or vector norms? In order to find how close the 2 vectors or 2 matrices are, and in order to find the convergence of sequences, we can use the notion of a norm. So if we go back to this, it's saying the average times the average of v1 and v2. Oh yeah, that's right. Yes, normal distribution. So yes, this is the average times the other average of the vector. So that's going to be well, 1 plus 2 plus 3 divided by 3. This will be 0.5 um, 1 oh 1 plus 1.5 divided by 3, and this will equal the norm, I guess. 6 divided by 3 equals 2, and then 3 divided by 3 is 1. And it says, 5 times exactly as demonstrated with the following code snippet. Yeah, okay. So that's going to be, and then you find the dot product of these. So that's going to be 2 times 1, 2 times, wait, what? 1, 2, 3, 0.5 times that. It's going to be a half in all those. And let's get the dot product of v1 and v2. So the dot product of v1 and v2 is 1 times 0.5 equals 0.5. 2 times 1 equals 1. 3 times 0.5 equals 4.5. 4, 2 times 1 is 1. 4, so it's 5, 6. So that's the dot product. No, that's the sum of, and then no, that's right. That's the dot product. Yeah. Okay, so if that's the case, then the dot product. Let me just check that actually. Dot product. I think it's that, isn't it? Sum of it's multiplied. 2 times 1 is yeah, okay, and then it's the sum of all the multiplications. Whoops. Okay. No, I did do that. 1 times 0.5 is 0.5. 2 times 1 is I'm an idiot. Okay. 2, 3, 1.5s is 4.5. So it's going to be 2, 4, 5, 6, 7. Right, so that's the dot product. And then it's saying where's the screen? There it is. Yeah, then it's saying divided by the normal of a vector. Well, okay, we know what a normal is, but I just want to actually double check this. Let me open up Python for a second. Pi. Let's go. Oh well. Let's see. Import numpy as np. Pip. Well, okay. Let's not do that here. Let's go here. New file test.py. Import numpy as np. I will make the screen a bit bigger. Then you're going to be np dot. What was it again? Lionelg.norm. Lionelg.norm. V1 was. Oh yeah, nice. That's good. Right. So let's see what that comes out as. Oh, you have to do this now, don't you? That's the one. What do you say? 3.7. So that's, what is that? So 1 plus 2 plus 3 divided by 3. Let's try that. Oh, not that then. So I wonder what the norm is then. V1. What does Lionelg.norm do in Python? Norm of a vector or a matrix. It takes order none. So just to calculate the. Okay. Used to calculate one of the 8 different matrix. Okay, let me just close this window quickly. It's so funny. I wonder if people actually writing this, like they must be so involved with maths, it just makes total sense to them. It's used to calculate one of the 8 different matrix norms. So I need to know what a matrix norm is. Is a vector norm in a vector space whose element are matrices of given dimensions. Suppose a vector norm and a vector norm are given. Any m times n matrix A induces a linear operator from Kn to Km. Standard basis and wonderful. Oh, this is a bit intense. Like what? Can't be that hard. Who writes this stuff? Let me read this. A matrix norm is a function, okay, satisfying. It's a function satisfying. That's what it says. A matrix norm is a function. This is the magnitude of something in the ratio of C m times m cross product n. Damn, I mean, I need to know this stuff, but not now. Here, arc cosine is a trigonometric inverse cosine and is a function that computes the length of a vector. It's the magnitude of a vector. So why doesn't it say that on their documentation? So, okay, fine. So the length of a vector. So this is. Why are we doing arc cosine here? So let me go and get this whiteboard back up. So we've got the so vector 1 is going to be 1, 2, and 3. So let's say this is 1, 1, 1, 2, 3. So it's going to be 1, 2, 3. 1, 2, and 3. And then vector is half of that, so we've got 0, 5, yeah, there we go. 0, 5, wait, 1, 1, so it should be over here, sorry. Oh god, let's just roll it again. 1, 2, 1, 2, and then 3. 3 is pushing it back here. 1, 2, 3. Yeah, that's correct. That's more like it. So this one's going to be 0.5, 1, and then what's it? 3, so it's 1.5. 1.5, so it's going to be there. And so it's saying the dot product between them is 7. Well, actually, is it now? Let me just go and check that because my maths is really bad. So let's go do that. Let's see. V1 equals that. V2 equals 0.5 times that. And then we want to do V1 dot V2. 7. Alright, well, fuck me, my maths does actually work out there, goodness me. And then divide that by the final g.norm. Go on, help me out, yeah. She really like Copilot. It's very good. If you haven't got it, go and get it. It's awesome. Except that was wrong, so that needs to be times v1, v2, that's correct. Norms. Let's see what this says. 1. 2 times 1. Product of norms is 7. Product of norms is 7. Oh, that's interesting. V1, V2, dot product divided by... So here, arc oh, I haven't done the arc cosine. Oh yeah, arc cosine is... cosine of 1. Ah, this makes so much sense now. Right, yeah, yeah, okay. I see it, I see it, I see it. Yeah, I can just do it here actually. Let's just do it. np.arc cosine, and that should be actual 0. And it will be. Yeah, so the arc cosine is, let me just think. I have to remind myself of trigonometry here. Gosh. So it's going to be, what's, it's going to be of 1. So what's the angle of 1? 0. Oh, I see. What's the distance between the two? I see. The angle between the two. 0. I see. So that they are literally equal. So that's what that one's saying. Jeez Louise. Right. um, there's not sure exercise after reading this chapter. You can change W to, no, it's fine. Okay. Yeah, and then it kind of talks you through all this stuff. So that's that's awesome. Then um it's saying you can use the actual iris data set, and this is the graph. It says it's going to work because it's linearly separable. Um, and then this is the error thing I was saying. So basically, it's number of updates. Um, well, okay. This is related to the errors. It says misclassification errors versus the number of epochs, number of updates. I don't know. But anyways, it gets worse before it gets better. Um, and I talked about that funny thing where if you don't have linearly separable, it can still work, but it's not reliable, especially when you have this weird learning rate scale. Yeah, and this is drawing this separation for some reason. I don't know why. Just to kind of I think it's how to prove that the data is separable. In fact, I don't think it's. Yeah, it doesn't show you the mass of that, but I guess it's just yeah, drawing a line and filling the above and below. Um, yeah, so Adeline, adaptive linear neuron. Uh, well, we just have to consider what that's trying to say. So let's go over here. Adaptive linear neuron is like the linearity of that line or that decision making is going to change with respect to something, which is how I understood it. Um, Published by Bernard Widrow and his doctoral student Ted Hoff. Okay, cool. Uh, this linear activation function is simply the identity function of the net input, so that is equal to z. So the net input function was the dot product function plus, I have to remind myself that I think it was plus bias. I should also write it here. So the difference between them is before we had this dot product or net input and go straight into there, whereas this one, activation function here, identity, the identity is a strange word, and I haven't used that before, and then that gets fed through the threshold function, the sigma that we did before. Yeah, okay. So the activation function is like more gradual, right? So it's like um, it'll activate more as the dot product increases and activate less as the dot product decreases, rather than just having this activation function. It's like it can be activated more, so it's, yeah, okay. So I'm trying to explain this to myself. Um, this is what this is saying. So this is where I wanted to get to. Nice to be reminded. I might actually take a short break in a second. We've got, yeah, almost an hour, so we'll get to an hour. So one of the key ingredients of supervised machine learning algorithms is to find objective function. That is to be optimized during the learning process. The objective function is often a loss or cost function that we want to minimize. In the case of Adeline, we can define the loss function L to learn the model parameters as the mean squared error between the calculated outcome and the true class label. So here's our beautiful new function. Let me just move this along again. So L is a loss function, and it takes looks like an array of weights and the bias, and it's got this sum of I equals 1, and then it's got the feature, the actual label minus the prediction, all squared. Okay. Now it says the term 1 over 2 is just added for our convenience and will make it easier to derive the gradient of the loss function with respect to the weight parameters. So when we're doing the partial differential with respect to W, the weight, it's saying that it's going to make it easier. Now I I totally get what they're saying, but I couldn't figure out why at the beginning. So this is the really interesting part, is why that has been said. The main advantage of this continuous linear activation function, in contrast to the unit step function, is that the loss function becomes differentiable. So we get to know the gradient of the function, or the values returned from the function. Another nice property of this loss function is that it is convex. Thus, we can use a very simple yet powerful optimization algorithm called gradient descent. It's convex, so I think there's convex is like that, isn't it? So I think it's trying to draw the diagram for us, and it's saying that it's going down, it's going down the negative gradient. So we've got the gradient, the change in, and it's going to go down this way instead. Yeah, that's that. So now it says it's differentiable with respect to W. So this is my first peeve because I don't quite understand it so well. If you've got W here but W is not used in here, it simply means that this function is attributed to the loss function when a W and B are passed in, but that you're not using any of those variables to do anything. And then I realized that the the sigma function has those things in it, because sigma, of course, is equal to, and I think it does say somewhere, well, because W is, so using gradient descent, we can now update the model parameters by taking a step in the opposite direction of the gradient. There you go, the upside down change thing. And it says W's update is equal to the existing weight plus the change in the weight, and B's is the B plus the change in the B, and I think that was the same as last time. The parameter changes, change of W and change of B, are defined as the negative gradient multiplied by the learning rate. So I think this is saying this is the new part. So it's saying, well, come back to this one because I think that's interesting. It's saying that the change in W is equal to the negative of that gradient, or that learning rate, sorry, which makes it negative. And then they want the inverse of that gradient for this function, right? And then the B is the same as well. To compute the gradient of the loss function, we need to compute the partial derivative of the loss function with respect to each weight, Wj. Now, it hasn't defined the loss function here, which I really don't like, and I wonder if it's because it's kind of relying on you to go back to what you'd originally put in before. Compute the gradient of the loss function. L is the loss function, so it's the loss function with respect to W. I see. So here it's also changed a few things because now we've got negative 2 over n. So to compute the gradient, we need to compute the partial derivative of the loss function with respect to each way. Similarly, we compute the partial derivative of the loss function loss with respect to the bias. Whew, okay. Um, okay. So I'm going to come back to this. I'm getting a little bit hot. Get some um, snacks and stuff, and I shall be back. But this is good to get back into this live streaming because I feel a little bit more, invigorated, revitalized. Anyway, speak to you later, and hope this has been interesting.